Generators and motors. Generators. So most of the energy that we use comes from changing mechanical energy into electrical energy using what we know as a generator. Generators rely on the relationship between electricity and magnetism. An electric generator converts mechanical energy into electric energy. Ørsted discovered the relationship between a current carrying wire and a magnetic field. He demonstrated that a compass needle will move when a current went through a wire nearby. This means that the current in the wire produced a magnetic field and that interrupted the magnetic field of the Earth and made the compass move. This was the first step to discovering the relationship between magnetism and electricity. And again, all motors and generators are built on this relationship. So this was a really big discovery. There's a YouTube video linked below on the Ørsted experiment. You can kind of see in this little picture here, there is a wire here with a current going through it, and we have the compass below. And when the current moves through this wire, depending on which way it's moving, whether it's moving left or right, it'll make the compass needle move as well. An electromagnet is a strong, temporary magnet that is created by inserting a piece of iron into a coil of wire and passing a current through the wire. So, an iron nail, we can see, iron is magnetic, so things will stick to it. So when we're looking at regular iron, the atoms in iron align themselves in different planes, so they aren't all lined up the same direction. This is important because if they all line up the same direction, you can see north and south here, we end up with this iron acting as a magnet itself. So it isn't attracted to other objects, but it is attracted to magnets because it has magnetic properties itself. Okay, so typically they're all kind of helter-skelter, out of order here, the north and south poles of the iron atoms, if you will. So they aren't magnetic. When we run a current through a wire that's wrapped around this nail, so this unmagnetized nail, it forces all of the atoms, the north and south poles, to align. Okay, so all of the souths are pointing this way and all of the norths are pointing this way. And that makes iron into a magnet. Okay. So when current flows through the wire, one end becomes the north pole and one end becomes the south pole. If we add more coils, so if we coil this tighter, the magnet becomes stronger. If we increase the current through it, the magnet also becomes stronger. If I reversed the current, so if I reversed the battery here and put the positive end here and the negative end over here, this will turn this into the south pole and this into the north pole. So it makes it opposite. Okay, so if we reverse the direction of the current, the polarity of the magnet changes. If we disconnect, the magnetic properties disappear. Electromagnets are used in lots of different things. So, for instance, of course, we talk about generators. They're also used in headphones. In old school VCRs to record, if you even know what that is. MRIs use electromagnets. And one big one that I can think of is if you've ever been to a scrapyard, they use a magnet to move things around, but they want things, whatever they're moving with the magnet, to be able to be released. So they use an electromagnet. So they turn the current on to like magnet things or attract things to the magnet to move, and they will turn the current off to release that item and place it on the ground. Other things could be trains. So they use it for high speed, like bullet trains. There's a bunch of different applications for this. All right, so Faraday from Ørsted's experiments, Faraday knew that electricity produces a magnetic field. So he asked whether a magnet could produce an electric field. So electricity. So Ørsted knew that electricity produced a magnetic field, and Faraday's asking, can we go the other way? So Faraday pushed a magnet through a coil of wire that was connected to an ammeter. So he coiled up some wire and then moved a magnet through the middle of those coils. As the magnet moved in and out of the coil, they did see a current being produced. And so this is how we produce electricity. So Faraday's experiment was also very important because Faraday showed that we can produce electricity using a magnet. Again, another video that shows Faraday's law linked below here. And I have a bunch of GIFs in this presentation, but in the form that I use to record my videos, the GIF isn't moving. So I've linked this below in our course website as well, so that you can see what this looks like. So magnets moving through a coil generate electricity, and a coil moving between magnets also generates electricity. So we can move the magnet, or we can move the coil in the experiment. What this shows is that this is a rotating coil. So it's spinning around on this axis through two stationary magnets. These are staying the same. This is the wire and an ammeter. And these are connected. So there's a positive and a negative lead here. The wire that's turning, comes from here. You can see it goes around in a loop and it ends at this coil. So we create a circuit. When this wire moves, we see a current generated. This is another picture and another GIF of the exact same thing. All right. So an AC generator. A coil of wire rotates in a magnet again. Okay, typically these are an electromagnet because we can make them really strong by increasing the current. The ends of the coils are attached to this circuit using two brushes and rings. So just to allow it to spin, this ring is connected to the wire, and to allow it to spin, there's a little brush that makes contact with this ring the whole time. So if we're talking about brushes, we're just really talking about that connection and allowing this to spin, but maintain contact. So this coil can be rotated using steam, water, or wind, something that generates enough movement for it to move in a circle. These wires rotate and electrons move along the wire in one direction. Okay, so they'll move based on where the wire is in relation to the north and south. All right. After half a rotation, so let's say this wire is kind of this way, and this is side 1 and this is side 2. After half a rotation, wire 2 is now over here and side 1 is over here. They flip halfway through. When they do this, the current moves in the opposite direction. So when side 1 is aligned with the south pole of the magnet, the current moves in one direction. When side 2 is aligned with the north side of the magnet, it moves in an opposite direction. This is very simplistic in terms of how it actually looks, but this will do for our Science 9. The more complex we look, we have to get to a Physics 30 kind of level of electricity and magnetism. So we're going to stick with this. When side 1 is pointed to south pole, it generates a current in one direction. Once it turns half a rotation and looks at the north pole, the current goes in the opposite direction. So with each full revolution of the wire, the direction of the current changes twice. So it'll go one way, the other way, and then once it gets back to its original position, it'll go the other way again. So the current is alternating. Alternating current, or AC, current is electricity produced in a generator where the current flowing from the generator changes direction regularly. Remember, it changes when the one side is aligned with the north and the south pole. Generators turn at a constant speed so that this current alternates 120 times per second, or aligns one direction 60 times per second. All right, so within 1 second, it switches 120 times. This makes what we see as like a wave. So when it heads in one direction, we can say that that is the positive direction of current or voltage, and our current will say, and then negative. So we can see that we have it moving in a positive direction, and then it switches and moves in a negative direction. And then it switches and moves in a positive direction and a negative direction. Positive, negative. This switch happens 60 times in a second. So from one direction back to that same direction, if you will, happens 60 times in 1 second. And we call that 60 hertz. Okay, this is the current that we use in North America. The reason that our appliances don't work in other countries, like in Europe, is they use 50 hertz. So the generators that create their electricity there turn at 100 times per second. They also use a different plug so that you can't mess this up, but we have a different alternating current here in Canada and North America. Again, the positive and negative values here just represent the different directions of flow. So why AC current? Well, because it travels as a wave, it's actually easier to transmit through the lines. We can increase or decrease the voltage using a transformer. Okay. So when we increase it, we can then transport it in a high voltage line. Remember, these have very little resistance and very large pushes, very large voltages. So the current is quite low, meaning we don't have to have a large number of electrons moving through. For use in our homes, though, from these wires, we need to step it back down from this really, really high voltage back down to something that we use. So, for instance, let's say in a generation station, electricity is produced at about, let's say, 30,000 volts. When it goes into our high voltage lines, it is stepped up to over 500,000 volts. So we went from, let's say, about 30,000 volts to 500,000 volts. Now, that's pretty large. So then when it comes into our city, there are substations that are going to step it back down. And then it'll step back down to outside of our houses. You might have a power box or a transformer at your house, and it'll step it back down to what it's coming into our house at, which is 220 and 120. All right, so it generates at quite a high voltage. We step it up to go through the lines and be transferred throughout the province. And then we'll step it down at a few different stations along the way. All right, so that was AC current. Again, it comes out as a wave. It's alternating between positive and negative. So DC current is a current that flows in only one direction. Okay, so ours was alternating before. DC, it only goes in one direction. A generator that produces DC current is called a dynamo. Again, we have this rotating loop of wire, but it is connected to the circuit via this thing called a commutator. Okay, a commutator serves to reverse the induced current as it changes direction, making the current flow in only one direction. So what it does is, let's say we want this direction of current. It allows that. When our loop is going to rotate and would typically have rotated to become a negative current, Our commutator takes that into account and switches it so that it will become positive again. All right. Again, this is a GIF on our course website. Commutator just has this little break in the line here. Okay. It's like a little split ring. And when it's on one side, it's helping to maintain positive, and on the other side, it's again helping to maintain that positive voltage. Okay. Again, stop and watch this video before you go. It is really, really good at describing AC and DC generation. And shows what that commutator looks like to help switch the direction of the current. So pause this, open up a new window, watch this YouTube video, and then come back. Again, a commutator is kind of drawn here. This is another GIF on our course website. When the brushes touch the metal rings, again, they're brushes that were inside those metal rings to make sure that as the wire loop rotates, it still maintains contact with our entire circuit. So when the brushes touch the metal rings, electrons flow through the circuits. When they touch those gaps, electricity stops. Current momentarily stops. When the rotation continues again, current through the coil has been reversed, but so has the connection. So this one was connecting maybe when it was a positive to this. All right, it looped around. And then when it loops around again, it breaks connection. This other side, I guess, would have been here, and it now becomes the positive connection. And this one that just finished being positive, looped around and stopped, is now negative. It loops around again. Okay. And they keep switching back and forth. And this allows the connection into our circuit to maintain a positive direction of flow. Again, those insulating gaps are important because they stop it and allow these sides to keep switching between positive and negative. This allows a constant current. So we see here, again, our AC current, okay, and DC current. DC current is actually just a bunch of bumps. Remember, it stops conducting when that insulator hits. So what we're going to see is a bunch of bumps. And the average of them becomes this DC current line. Okay, so these spots here are where those insulators in the commutator are connecting with our circuit. Okay, now to make sure that we get less of these gaps, what we end up doing is we put generators together, and we'll make sure that this one, I guess I should use a different color. That would be more helpful. If this one is doing this, then the average gets much closer again to this line here. Okay, so they just keep overlapping them as much as possible to get a more direct or maintained current. An electric motor converts electrical energy into mechanical energy. Electricity is used to spin that coil of wire, my goodness, between the poles of a magnet. So instead of using water, wind, steam to turn the coil, we're using electricity to turn the coil, which then generates mechanical energy or movement. All right, so the St. Louis motor is a DC motor. These run on batteries, so these would be small things that we have to put a battery into to make run, like maybe one of those little personal fans that you would carry around or something like that. So battery provides DC or direct current to the circuit. The current flowing through the coil turns it into an electromagnet. So this is the coil here. All right, we can see where it's been wrapped around. Okay, coil turns into an electromagnet. This current causes a magnetic field, and One side becomes a North Pole maybe, and one side becomes a South Pole. Then what's around this electromagnet is a permanent magnet. Okay. This permanent magnet, of course, will be attracted, the North Pole will be attracted to the South Pole. So the arm will rotate to align itself. All right. Now we're using a split ring commutator so that we can now switch to the opposite. So once the south and north align, the south becomes a north, and then they're repelled. So this north wants to rotate again back down to the south. And then as soon as it does that, it becomes south again, and it wants to rotate up and be attracted to the north. So we get this constant rotation because this keeps flipping in perfect time. Okay. So this produces, because it's on an axle, it produces movement and creates mechanical motion. All right, so the brushes allow this to maintain contact to our battery or DC current. The commutator allows this to keep flipping between north and south, and it the electromagnet is produced by this iron and coils of wire. The permanent magnets also help to keep it spinning, creating those attractions. Now, of course, I just did that in 2D without any movement. I think that this is a good video that shows how we can produce that St. Louis motor. Again, the St. Louis motor is just the most generic, straightforward DC motor that we can produce. An AC induction motor gets a little bit more complicated. Okay, so we'll try and keep this simple, but get enough information out of it to understand how an AC motor works. Okay, these were designed by Tesla. Sounds familiar? Tesla cars. AC motors are usually found in larger appliances where more mechanical energy is needed, or things that are just plugged into the wall. These are made up of a central rotor that is allowed to rotate around and around. Okay, it's a rotating core with a ring of non-magnetic. It's important that it's non-magnetic to begin with. Conducting wire wrapped around it. All right, so we've got wraps around it, and it's connected to this axle. The fact that it has an axle is what allows it to create mechanical energy. This central rotor is placed within what's called a stator. The stator is the stationary part that surrounds the rotor. It contains an electromagnet. This is connected to AC power and generates a rotating magnet. So, again, this would start north and maybe south. When the electrical energy is applied, the magnetic poles of the stator and the rotor cause the rotor to spin. So let's say that this was a south pole. It would be repelled here. All right, so it would start to maybe rotate this way. Let's say that that's the way our motor is rotating. Of course, it wants to rotate that way because it's going to be attracted to the North Pole here. However, this is AC current. So as it's rotating, it gets to a point maybe here, the point of no return. So our south has moved all the way up to here. Okay. And our current switches. So this becomes south and this becomes north. And of course, this is like, hey, I don't want to be here anymore. So it keeps trucking and moves really quickly along. So this repulsion is like a push. So it gets a push on this side and it gets attracted over here. And just as it thinks it's going to just stick with this North Pole again becomes a south and this becomes a north. And again, our south has moved to here now. And it's like, ugh, I don't want to be here. And so it pushes it and it moves it around one more time. And it just keeps spinning in that way. So you can think about it as a push. Okay? Every time this one point gets to one side, it gets a push. And then it goes around to the other side and it gets another push. And it goes around to the other side and it gets another push. And it keeps it turning. Again, this is the axle. It's like it's coming straight out towards you here. That's what keeps it turning. I forgot to add the extra page here of practice. Don't forget to take a look at the learning guide here. I would highly recommend that you take the time this today to watch the videos that I've posted on how the generators and motors work, because they do a really great job of explaining it and actually showing it move rather than me trying to draw diagrams and cluttering it up like I just did. Okay. There's also some extra practice in your textbook. As always, I will make sure that I post that below so that you can take a look at it, but it would be at the end of topic 6 for electricity.